My name is Soto, and I am a statistics major with a minor in computer science. And today I will present to you Disproving Conjectures in Spectral Graph Theory with a little help from AI. This has been a collaborative effort between myself, my colleague Peter Marlin, and my mentor Sebastian Chauvat. And with that being said, let us begin. I would first like to denote or explain the concept of a graph. A graph is an abstract model of a network. There are many examples of graphs around us, such as social and communications network. And on the left, you can see there's a graph. There, the circles denotes or shows the vertex. They're called vertex or vertices, and the lines between each vertex and vertices are called edges. Now we use linear algebra to help us study such graphs. An example would be what is below the graph, the adjacency matrix, which is a square matrix where the rows and columns are labeled by the vertices. Each coordinate denoted by xy denotes the number of edges it takes to get from vertex x to vertex y. And from the adjacency matrix, we can extract what are called eigenvalues, which hold information or special properties about each graph. In 2021, Adam Zoff and Wagner published a paper called Construction of Combinatorics via neural networks, which shows how to use AI to construct construction for examples for conjectures in graph theory. Now, the way he did this is that he first started with an empty graph, which he then put it into the neural network, which is shown on the top left, and it output a probability, which showed or told the neural network to either add or remove an edge based on what we call a reward function. This is an iterative process where we reward our neural network based on desired actions and penalize it based on suboptimal options, guiding it to our objective, which is disproving a conjecture. Adam Wagner's first example was a conjecture proposed by Austrisch and Hansen in 2009, which states that given a graph G, and with n vertices, which are greater than or equal to 3, a largest eigenvalue, either known as lambda1, and a magic number mu, that the sum of the largest eigenvalue and the magic number is at least the square root of the number of vertices minus 1 plus 1. Adam Wagner's neural network managed to output a graph of 19 vertices with the largest eigenvalue being the square root of 10 and a magic number of 2. Under these conditions, this graph does not follow the conjecture above, i.e. meaning that this is a counterexample to the conjecture. In 1957, Collat and Sinigowitz managed to prove that given the average degree of a graph, d hat, and the maximum degree, delta, that the largest eigenvalue is between the average degree and the maximum degree. This was a motivation for our first toy conjecture proposed by my professor. And before I move on, I want to explain what is a toy conjecture. A toy conjecture is essentially a conjecture that has already been disproven, or is a low-hanging conjecture that is easy to disprove. And the purposes of this conjecture is just to give a baseline if our neural networks are able to output a graph that could disprove such conjecture. So our first toy conjecture proposed by my mentor, Sebastian Chauvat, states that the largest eigenvalue is at least the average of the average degree and the maximum degree. Given Adam Wagner's neural network and a customized built reward function by myself, I've managed to output a graph on 9 vertices, which is showcased on the left, and on the right it is a snippet of the code that was used to extract the following properties of the graph. This graph has the largest eigenvalue of less than 4.4, 4.3 something, specifically, average degree of 3.55555, and a maximum degree of 6. And under these conditions, this graph manages to not follow, or this graph does not follow the conjecture above. Therefore, it is a counterexample to the first toy conjecture above. Our second toy conjecture is essentially the exact same thing, but just with the inequalities switched. That states that the largest eigenvalue is at most the average of the average degree and the maximum degree. And this is the neural network output the graph again on 9 vertices with average degree of 2.66666 and a maximum degree of 4, and the largest eigenvalue being 3.418. Go on. And under these conditions, again, we managed to obtain a counterexample to the second toy conjecture. Now, for our first non-toy conjecture, otherwise known as a series conjecture, now, I would first like to denote the concept of the energy. Energy is the sum of the absolute values of the eigenvalues, and with this, This being said, I would like to introduce our first serious conjecture, which is proposed by Coutinho in 2025, which states that let G be a graph with n vertices and alpha, independence number alpha, states that the energy is at least 2 times the number of vertices minus alpha. Our best construction that we were able to obtain is a graph that is essentially just 2 graphs, complete graphs with 5 vertices, which is connected together by perfect matching, and essentially just making one graph on 10 vertices, independence number of 2, and under these conditions, we managed to obtain equality with an energy level of 16. And you can see below, we get 16 as well for all the combined other components. Unfortunately, this was not able to be a counterexample, but it's just really close, just off the cusp of being a counterexample. And so you're not going to find it, but we then go to our final serious conjecture proposed by Brouwer in 2012 that states that let G be a graph with n vertices, the cardinality of the edge set E, and the sum of the k largest Laplacian matrix eigenvalues S sub k of G. And it states that the sum of the k largest eigenvalues is at most the edge set cardinality plus k plus 1 choose 2 for any natural number k. And this conjecture has been proven for the cases of k equals 1 and k equals 2, but not for k equals 3, which was what we managed or hoped to disprove. And we managed to get the output of the left graph on 12 vertices, which has the 3 largest eigenvalues of the graph, or the Laplacian eigenvalues of 22, and with edge set B at 16, and k plus 1 in this case 4 choose 2 equals 6, we managed to obtain equality as well. Just again, right off the cusp, we had a counterexample, which unfortunately we were not able to find a counterexample for the energy or Brouwer's conjecture. But with that being said, my future direction is that I hope to one day be able to advance my studies. And since I'm in the 4+1 program, I hope to work with a graph theorist and a specialist in neural networks, and hopefully together all 3 of us collaborate in a way where we can build a neural network, specifically a graph neural network, to be able to disprove such conjectures above. And that is my future work. And that would be it. Thank you so much for